A 112-gram hockey puck sent sliding over the ice is stopped in 17 meters by the frictional force on it. If the puck had an initial speed of 6.25 meters per second, what was the magnitude of the frictional force? Of course, since the puck is in motion, this would be a kinetic frictional force. The mass of the puck is 112 grams. The displacement in the x-axis, or s of x, is 17 meters. The initial velocity in the x direction, or vx initial, is 6.25 meters per second. The final velocity of the puck, vx final, is 0. Since the puck is on a horizontal surface, neither moving upwards nor downwards, v sub y is 0. The puck is at rest along the y-axis. Looking at the forces, there is no pushing force. The only x-axis force that there is the force of kinetic friction. The force of kinetic friction is the net force along the x-axis. The unknown. What was the magnitude of the frictional force? So we write F sub F, or the force of kinetic or sliding friction, is what? The equation. Since we're asked for the force of kinetic friction, we're tempted to write the frictional force is the coefficient of kinetic friction, mu sub k, times the normal force. But when we look at our givens, we see that we do not know the coefficient of kinetic friction. Therefore, this is not the correct equation. So what is the correct equation? The velocity of the puck along the x-axis is changing. Therefore, we can use Newton's second law. F is ma. So we write the second law along the x-axis. The net force along the x-axis, F net of x, is mass times the acceleration in the x direction. The net force along the x-axis is just the frictional force, and it's negative. Do we know the mass? Yes. Can we find the acceleration along the x-axis? We write down the equation for acceleration. A sub x is v sub x final minus v of x initial divided by the time. But when we look up here, we do not have the time. Instead, we have the displacement along the x-axis. So this is not the correct equation for the acceleration. Noting that we know the displacement along the x-axis is 17 meters, we can write the time not known equation. Vx final squared is Vx initial squared plus twice the acceleration along the x-axis, a sub x, times the displacement along the x-axis, s of x. We substitute and solve for the acceleration along the x-axis. V sub xf is 0, so we write 0 squared is Vx initial is 6.25 meters per second. So we write 6.25 meters per second squared plus twice the acceleration in the x direction times the displacement along the x-axis, s of x. That is 17 meters. This gives us that 0 squared is 39.06 meters squared second squared plus 34 meters times a sub x. We solve. A sub x is equal to minus 1.149 meters per second per second. That becomes a given. Now we can solve for the frictional force using Newton's second law. We note that F net of x, by looking at our force diagram, is the frictional force. So we write F net of x, we substitute in for the frictional force, it is negative. Minus F sub F is mass times acceleration along the x-axis. Then we have minus F sub F is 0.112 kilograms. We must change the grams to kilograms times minus 1.149 meters per second. Remembering that a kilogram times a meter per second is a newton, we get that the magnitude of the frictional force, F sub F, is 0.129 newtons.